All right, so we're going to come up with kind of a useful new idea here. So the first two definitions written down here are ones that we've used in a few places already, closed under addition and closed under multiplication. This was part of the binary operation idea that we started with in this chapter. So a set is closed under addition if for every two elements in the set, S1 and S2, then the sum, S1 plus S2, is also in there. And then closed under multiplication is similar. Something is closed under multiplication if for every pair, S1 and S2 in the set, the product is in the set. All right. So we're going to use those in 1 minute with this lemma we see. But first, a definition. So if we have a ring R, and we have some set S. It's called a subring of R if it's a subset of R, so it's completely contained in R, and it's a ring in its own right. Okay, so S is a ring means it satisfies all those ring properties that we had in when we defined a ring. But this lemma tells us there's actually a shorter way to check this. If S is a subset of R and R is a ring, we don't need to check all the ring properties. All we need to check are these four: closed under addition, closed under multiplication. We need to know that 1 is in S and that additive inverses are in S. And if we know those things, then automatically a subring of R. So that means S is a ring. This little lemma is sometimes called a subring test, and it's a way to take kind of a shortcut to not have to verify all the ring properties, just these four little ones. And our idea here is we want to figure out why. Why do the rest of them hold? And if you want to see this in action, you can go back to that example of the set of all numbers that were of the form a plus b root 2, where a and b were rational numbers, because we kind of used this lemma without really writing it down. So now we're going to write it down so we can use it easily in the future. All right, so let's talk about why S is a ring. So that's our question. Why is S a ring? Okay, so parts 1 and 2 up there, so number 1 and number 2 up, say S has two binary operations. Okay, because R is a ring, the addition is associative. Multiplication is associative. Multiplication distributes over addition. And addition is commutative. Okay? Now, all of these things hold for addition in R, but we can also add things in S, and we're really doing the same thing. It's like adding integers instead of adding rationals, or adding real numbers versus rational numbers. If we know that addition is commutative in any of those settings, if we knew it's commutative in R, I should say, then we know it's also commutative with integers, because integers are real numbers. So if we know it holds in R, the bigger ring, then it definitely is going to hold in S. So all of these will then also be true in S. Okay, so S will have associative addition, associative multiplication, it will have the distributive property, and addition will be commutative. That takes care of a whole lot of our ring definition right there. All right, so what's left is we know 1 is in S by, let's see what number it was up here, property 3 there. And we know S has additive inverses by 4. Okay, so there's 2 more of our ring properties. The only one that's left is that we need to show 0 is in S. Okay, that's the only ring property left. The ring properties, the rest of them we've taken care of. There are 4 of them up here, associative, associative, distributive, commutative, and there's 2 more here. 1 is in there, additive inverses are in there. So all that's left is that 0 has to be in S. Okay, so why is 0 in S? And the answer here is because if A is in S, minus A is in S, and since, and that was by property 4, right? And since S is closed under addition, A plus minus A is in S, which means 0 is in S. And so all we need is to check that S is closed under addition and multiplication, that those operations make sense for S. We need to make sure 1's in there, an additive inverse is in there, and then we're done. That's all we need to say that S is a ring. And so this is a really handy thing. Let's do some examples. So some quick ones are things like, so let's take R is a ring. That will be our biggest ring in our setting. So Q is a subset of R that is closed under addition and multiplication. So if I add 2 rational numbers and I get a rational number, and if I multiply 2 rational numbers, I get a rational number. 1 is definitely a rational number, and for any R rational number in Q, minus R is also a rational number. Okay, so Q is a subring of R. Okay, how about Z? Z is a subring of R for the same reasons. Closed under addition. If I add 2 integers, I get an integer. If I multiply 2 integers, I get an integer. 1 is an integer. And if A is an integer, then minus A is also an integer. And so the integers, Z, is a subring of R. Okay, we could also say Z is a subring of Q. That would be fine for pretty much the same reasons. Okay, and let's talk about that one we did before. So S, I'm going to name this set S, set of all A plus B root 2's, where A and B are rational numbers. This is a subring of R also. And if you go back to where we talked through that example, you'll see that these were exactly the kinds of things we were talking about there. All right, so I want to give you one that's not a subring. So let's do a non-example. If T is the set of all A plus B root 2 plus C root 3, where A and B and C were real numbers, this guy is not a subring of R. It's a subset, but it's not a ring. Okay, and why is that? So if I add 2 things of this form, if I have an A plus B root 2 plus C root 3, and I add it to another one, a D plus E root 2 plus F root 3, I can combine like terms and that sum's going to be fine. I know that 1 is in here. I can choose A to be 1 and B and C to be 0. I also have additive inverses. I can just negate A and B and C and I have an additive inverse of any element I want. It's the closed under multiplication that's a problem. So try multiplying a couple things. A plus B root 2 plus C root 3 times I should start with D plus E root 2 plus F root 3. if I multiply these out, what's the thing that I am going to be missing? So I'm going to have some nice things like AD. I'm going to have a BD root 2, right? I'm going to have a CD root 3. I'm going to have a bunch of other terms like this. And they're all going to be fine, right? AD is okay. Anything times root 2 is okay. Anything times root 3 is okay. But there's a big term that's missing here. There's a term that we get out of this product that isn't of the form a plus b root 2 plus c root 3. And I'm going to leave this as a little exercise for you to do and set up a multiple choice question about it so that you can continue this product out, find the actual product, and then figure out why this is a problem, why this thing is not a ring.